morning. It's always a immense pleasure to be here in Natal, and especially with like many friends and nice people. So I would like to start thanking the organizers and the sponsors for putting up this really nice conference once more. So today I'm going to talk about this work of ours on the minimal example of quantum nonclassicality without freedom of choice. This talk is based on this paper, which is joint work with Pedro Lawand, David Poderini, and Rafael Chaves. And before I enter into the details about this work, let me start with Bell scenarios, with familiar Bell scenarios, bipartite ones. So in Bell scenarios, we have two parties, Alice and Bob, and they're performing measurements on systems which were prepared in some special way, maybe. So we have these systems which are correlated, and then Alice in her lab, she can perform measurement X and obtains result A, and Bob in his lab can perform measurement Y and get outcome B. We usually assume that the parties don't know anything about their measurement devices or the systems they're measuring. So best description that one can have about the experiment that's going on is for them to perform like many rounds of measurements on the systems, which we assume were identically prepared in every round. And then they can estimate these joint probabilities of obtaining results A and B, given that they perform measurements Y, X and Y for all A, B, X, and Y. So this usually is the best description they have of their experiment. And then we can take all these numbers once we estimate them and organize them in a vector. Okay, so just like organize them as entries of a vector, and we usually call this vector like the behavior of the experiment. In general, they will observe correlations between the outcomes of the measurements they perform. So in general, what the party is going to observe is that the joint probabilities are not the product of the marginals. So the probabilities in the system, in the whole systems, are not independent. The outcomes are not independent. And we say that correlations are local, or they can be explained by a local hidden variable model if the probabilities can be written like this. If there is a lambda, a variable that we don't have access to, which is correlating both outcomes in party A and party B. So this is usual definition of locality. And now, okay. Now, let's suppose Alice and Bob, they share a quantum system. So let's say they share a quantum system in state rho. And when Alice performs a measurement on her quantum system, there's a quantum operator that describes this measurement. So let's say pi A is the measurement operator associated with outcome A of measurement X. And also the same for Bob. And we say that the probabilities admit the quantum model if there are states and operators such that the probabilities that they observe can be retrieved by Born's rule with these operators. So, as you all know, Bell's theorem says that there are quantum behaviors. There are behaviors that come from quantum systems that do not admit local hidden variable models. And also, as you all know, usual proofs of this theorem rely on examples of strategies, of quantum strategies that cannot be explained by a hidden variable model, usually by means of violating a Bell inequality. So you have a quantum strategy that violates a Bell inequality, then you know that the behavior cannot be explained by means of a local hidden variable model. Now, I'm going to associate this with a different tool, which is more common in causality theory, which are Bayesian networks and DAGs. A DAG is a directed acyclic graph. It represents causal relations between random variables. So in any DAG, we can have two kinds of variables: observable variables, the ones you have access to by measuring the system, and latent variables, the ones that you don't have access to for some reason. And just to be a little bit more precise, let's say all my variables are AIs, and for this interval where I is between 1 and n, we are going to label these as the observable variables, and then from n to n plus 1 to p, these are the latent variables. And then once we have a DAG with all these this graph, I hope it's going to be clear in the next slide when I'm going to associate this with Bell scenarios. So we say that a probability distribution, a joint probability distribution of all these variables, they admit this causal relation that is embedded in the DAG if they can be written, the probability can be written like this. So it's a product over all probabilities of all variables. And these probabilities are conditioned on the parents of these variables. And the parents, the set of parents is the set of variables such that an edge is coming from the parent and going to this variable AI. And also, you take this product, but also you have to sum over all latent variables, because these are the ones that we don't have access to, so we just marginalize over them. And one example is this DAG here. This is the DAG which is associated with the Bell scenario I just showed you. So here we have 4 observable variables, x, a, y, and b, and one latent variable, which is lambda. And the classical model associated to this DAG, according to the rule I just showed you in the previous slide, is this one. So the joint probability of all variables is the product of all probabilities of each variable and condition on the parent of that variable. So lambda, no parent. There's no arrow coming from anywhere to lambda. So it's just P of n lambda, the same with x, the same with y. So P of x, P of y. But for a, there are 2 arrows, 2 edges coming from different variables to this variable. So probability of A is conditioned on X and also conditioned on lambda, and the same for B. Okay? So this is exactly the same as the local model for the bipartite Bell scenario. The main difference here is the way I presented before, it was like conditional probabilities, but if you just take like P of X and P of Y and divide over here, then you just fall into the same definition that I showed you before. So these things are related, so that we can associate these DAGs with scenarios where we can study correlations between random variables. Okay. And why am I making this association? Because this is going to be important for us. So notice that here, in the simplest Bell scenario possible, we have 4 observable variables. Okay, x, a, y, and b. All right. So another definition: let C of G be the set of behaviors that are compatible with a certain DAG G. Okay, the ones that follow this rule that I just showed you. Let's say we have 2 DAGs, G1 and G2, such that the sets of classical behaviors of both are the same. I'm going to define an equivalence class based on this. Okay, so I'm going to say that these 2 DAGs are Markov equivalent if the sets of classical behaviors are the same for both of them. Okay. And now we're going to consider all DAGs of 3 observable variables. The one that I showed you before has 4 observable variables. So now take all the ones that have only 3 observable variables, but as many latent variables as you want. Okay. And there's a very nice result by Evans that says that there are only 3 interesting non-equivalent scenarios, and they are the instrumental scenario, the triangle scenario, and the unrelated confounder scenario. So let me go through all these 3, and let me show you why I think these are very, very interesting. So the first one is the instrumental scenario. So the instrumental scenario is a bipartite scenario. We have Alice and Bob. They share a composite system, Alice can perform a measurement X on her system, obtain a result B, but she can announce a result A, but she can announce this result to Bob. Okay? So in practice, it means that Bob can get this information from the result and use it as a measurement choice, so he can perform a measurement on his party. Okay? In principle, he has no choice. There's no why, but he can use this information from Alice to adapt his measurement system, his measurement device. Okay? So the DAG associated with this scenario is this one. So we have a latent variable and 3 observable variables, X, A, and B, but we also have an arrow from A to B. Okay? So we have this direct cause between these two variables. This scenario is very important for causal inference. It has many applications. It's very well studied in causality theory. And this is a simple scenario where we have both direct and indirect causal relations. So we have these indirect causal relations between A and B that comes from the latent variable, but also we have a direct causal relation because we have an arrow going from A to B. Okay? So we have both these causal relations in this scenario. And if we just apply the same rule that I showed you before, we see that the classical model associated with this scenario is this one. So we sum over lambda because it's a latent variable. A depends on X and lambda, and B depends on A and lambda. So it's slightly different from the Bell scenario that I showed before. And the quantum model is something similar. We have a shared quantum state instead of the lambda. The quantum system here is the latent variable in this sense, and measurement operator for Alice, measurement operator for each result of Bob, but it can depend on the result that Alice got before. Okay? And in this case, let's say that the outcomes are binary, so they can either be 0 or 1. It's easier to work with correlators than with the probabilities. So let's define these correlators, just like if the outcomes are the same, we sum the probabilities. If they're different, we subtract the probabilities. For AB and also for A, we just like put a minus sign if A equals to 1, or 0 if it's equal to 0, or a plus sign if A equals to 0, and the same for B. And with these correlators, we can define this inequality here in the case where the outcomes are binary and Alice has 3 measurement choices. Okay, this is the so-called Bonnet inequality, and it holds for all classical behaviors. So one way of showing like quantum non-classicality in this case is coming up with a quantum strategy that violates this inequality, and this is exactly what has been done. So people like our host and our next speaker, they managed to find a quantum strategy and also observe this in the lab. So they managed to see a violation of this inequality of up to 3.82. Okay, so this scenario here is a simple scenario where you can see like quantum advantage, the quantum non-classicality with three variables only. And also there's the triangle scenario. Triangle scenario is a tripartite scenario where the parties share systems, but only in a bipartite way. Okay, so we have a shared system between Alice and Bob, between Bob and Charlie, Charlie and Alice, but not one system between all of them. Okay, so these are all independent systems, and there's no measurement choice by any of them. Okay, they only perform the same measurement all the time. The DAG associated to this scenario is this one: 3 observable variables and 3 latent variables. This is a scenario which is cool because we don't have like direct causal influence between observable variables, but we have many bipartite latent variables which are independent. Okay? The classical model is this one. So A depends on only 2 of the latent variables, the same with B, the same with C, and we sum over the latent variables. Just for comparison, if I had like a tripartite Bell scenario, usual one, I would have a classical model which is like this: the same lambda appearing in all of the terms. Okay, so it's just to like to be very clear that in this case here, A depends on beta and gamma, but not on alpha, and so on and so forth. Okay? So it's a different scenario, a bit harder to work on. Okay? And the quantum model, we have three quantum systems, three bipartite quantum systems that share between the parties, and measurement operator for each party. Okay. So in this case, quantum non-classicality is also well known, has also been observed. Okay. The strategies, the known examples that we have to date require outcomes which are not binary, which have to have like 4 different values. Okay. And one point which is really nice about this scenario is that in usual Bell scenarios for like standard Bell tests, it's crucial that the parties can choose among different measurement possibilities. Okay, and here there's no choice at all. So in this scenario here, you don't need the freedom of choice assumption. So it's really nice because of this. Okay, so no freedom of choice assumption is necessary in this scenario here. And finally, let's go to the star force show. Okay, the third scenario that in this list of 3 scenarios is this one, the unrelated confounder scenario. So here we also have 3 parties, a bipartite system shared between Alice and Bob, another one between Bob and Charlie. They don't have measurement choices. Bob performs a measurement, obtains the result, and he announces his result to Alice and Charlie. Okay? So in practice, Alice and Charlie can use this information as an input into their boxes. Okay? So this is the scenario. May seem a little strange, but actually there's a familiar example where this happens. I'm going to tell you. So just for the sake, the DAG of this scenario is this one. So we have these 3 observable variables, 2 independent latent variables, and also direct causal relation from B to A and from B to C. Okay. So this is a very simple scenario where we have both direct and indirect causal relations, just as in the instrumental scenario, but also we have latent variables which are independent, as in the triangle scenario. So it has like ingredients from both of these things. Okay. And this scenario is related to the entanglement swapping protocol. So we have like a central party measuring a system and then announcing the result to 2 different parties. Okay, so it's not as strange. It's familiar in some sense. Okay. The classical model associated with this scenario is this one. Same thing, like as we had before. Like A can depend on B and on gamma. B can depend on alpha and gamma, not on any observable variable, but C can depend on B and alpha. Okay. And notice that we're giving a lot of power to the classical model. So we have communication, but also have like independent sources, but we don't have measurement settings. So the classical model here is quite powerful. And this is the quantum model, just for the sake. Okay, so we have like 2 bipartite systems and measurement operators. So the point is, when we first when we first noticed this scenario, we didn't know if the classical model was super powerful or not. So the first question was, is there any non-classical behavior in this scenario? Because it may be the case that the classical model recovers all possible probabilities in this case. Okay, so it took us quite some effort, but we showed that yes, there is non-classical probabilities in this scenario, ones that cannot be recovered by the classical model. But then the question was, is there any quantum behavior in this scenario which is non-classical? Because the first example that we had is easily non-quantum. It's like a peer box in this scenario here. Okay, so the second question is there any quantum non-classical behavior here? And the answer is always yes. And this is what I'm telling you a bit here, some of it here now. Okay, so the proof relies heavily on quadratic programming. okay? Because contrary to usual Bell scenarios, the set of classical behaviors here is not convex. So we cannot use the usual tools that we usually apply to solve these problems, like linear programming and SDPs. Here we have to go to quadratic programming. Okay? And let's consider a scenario in which all the observable variables are binary, so 0, 1, and let's define some correlators as well, because the outcomes are binary. So let's define correlators for A and C given B, for B, A given B, and C given B. Same way as I did before. Okay? And let's focus on a bipartite slice of all possible, like of this state of possible behaviors. Let's focus on a bipartite slice. So I'm fixing like many correlators. I'm letting 2 of them not to be fixed, this E plus and this E minus. All the others are fixed. It's going to be clear why soon. And then we, after a lot of try and error, we came up with this inequality that holds for all classical behaviors in this scenario. So it's not like pretty or anything. Like all these numbers, these coefficients were found by like very try and error, like really. So it's very artisanal inequality in this sense. But we managed to show that this inequality with this bound here holds for all classical behaviors. And then let's consider the following quantum strategy. Let's say both quantum systems are preparing this state, maximally entangled state. Let Bob perform a measurement, which is a projection in some non-maximally entangled state. Okay. Well, you can choose theta, but you can vary theta. So we have this one parameter family of possibilities here. But let's say Bob performs a measurement which is partially entangled. Okay. And remember, like Alice and Charlie also measure, and their measurement can depend on the result that Bob obtains. So Bob is projecting, he either like gets a positive result or fails. Okay, so he only has these 2 possibilities. But depending on the result, Alice and Charlie can perform different measurements. It's either sigma x or sigma z. Okay, they cannot choose. They have to perform the measurement according to the result of Bob. All right. So if you compute the quantum probabilities associated with this strategy, so you have this. So this is why we fixed all the correlators to find that inequality, because all these correlators come from this quantum strategy, and the only ones that depend on some parameter are these ones in red, E plus and E minus. Okay. And then the quantum, if we just compute the quantum value, it depends on theta. If we maximize the value of this expression for theta, we find that for theta pi over 8, we have a quantum violation. We have like 2.69, and this is greater than the 2.56 that we had before. So we show that there is a quantum strategy which is non-classical. Okay. And okay, so first objective is accomplished, and then we ask ourselves, is this easy to observe in the lab? And the answer is not really. And then the following question is there anything we can do to make it easier to observe? And in fact, the answer is yes. So let me tell you a little bit of one trick that we can use here to make this easier to observe in the lab. And it relies on interventions. Okay. So now I'm going to say that Bob is going to make an intervention in his node. He is not going to measure. He's just going to fix as if he measured the system, but doesn't matter. He's just going to fix some value for B according to some rule that he wants, okay? But not measuring gamma and alpha. So if he does this, in practice, he's breaking this link, okay? Because he's not using the system. So the value of B doesn't depend on gamma and doesn't depend on alpha. So in practice, he's changing the DAG. The DAG in practice is going to be this one. So the classical model is going to be slightly different. And this you can do, like in the lab. This you can do with the same setup, okay? You can even measure the system. You just don't have to use the measurement outcome. You just like send some other information to Alice and Charlie. Okay? So this is very easy to implement in some sense, okay? It's the same experiment, but it gives different results, okay? Because when you do this, when you do an intervention, then you have these different probabilities. Now you have these so-called do actions in the probabilities, okay? So now if you do this, you break the correlations between A and C, and now the probabilities are going to change, okay? The model is going to change. So that you have different data in the experiment. You can have like classical marginals, which are of this form when you do B, when you make this intervention on B. And in the quantum model, you're just ignoring like the measurement of Bob. So here, like this is the marginal of Alice. There's no measurement of Bob going on. So it's as if Alice is just measuring the marginal system that she has, okay? The same with Charlie. But the measurement operator depends on the B, which was not the result of Bob's measurement, but just some number that Bob sent to her, okay? So the data is going to be different. Define new correlators for this case, and then consider the full data. Like you perform the experiment, usual experiment, measuring and sending the information, also the intervention rounds, where Bob doesn't measure but sends some numbers to Alice and Charlie as well. So gather the full data, you make this data fusion, and then assume, like again, that these marginals are 0 just to make life easier. And then for the same bidimensional subspace, we can find a new inequality which consider all these data, okay, from both rounds. And then this inequality holds for all classical models. It goes up to 3.0003. And then with the same strategy as before, we can find that this inequality goes up to 3.15. So this inequality is more robust than the previous one if you consider these interventional rounds. Okay? So this is more friendly to implement, not easy, but friendlier. Right? So to sum up, I told you that, well, some examples that extensions of Bell non-locality to these more general scenarios where you can have like networks and independent sources or even direct causal relations between observables. This is really cool and leads to new forms of non-classicality. There are 3 interesting non-equivalent scenarios with 3 observable variables: instrumental, triangle, and this one, the UC, the unrelated confounder scenario. In the instrumental scenario, we need 1 treat and 2 bits to have non-classicality. In the triangle scenario, as far as we know, we need 3 2-bit variables. So these variables, they have to take like 4 different values. Okay? And in this scenario that I showed you, the UC scenario, we only require 3 bits. Okay, so in this sense, this is why we call this a minimal example, because you cannot go lower than this. You cannot go lower than 3 observable variables, and you cannot go lower than 3 bits. Okay? Like if any of these like is not a bit, and this is why we call this like a minimal example of quantum non-classicality. All right. For you to test non-classicality in this scenario, in some sense, it's easier than in the standard Bell scenario because you don't need like full space-like separation between parties. You do have communication between Bob and Alice and Bob and Charlie, but you need space-like separation between Alice and Charlie. Okay, so you don't need like full space-like separation. You're relaxing somehow locality assumption, and also there's no freedom of choice here. So you don't need this other assumption, which is crucial in standard Bell scenarios. Okay. And to finish, I showed you that interventions and data fusion can lead to more robust tests of non-classicality in quantum networks. So for this, I thank you very much.
Thank you very much for the nice talk. Are there any questions? Yes.
Could you comment on the relation between using and not using the interventions? Is it the same thing you're analyzing, or is it extra assumptions?
Assumptions in what sense? I mean, it's not really assumptions, but it's a different experiment. So, and it's gonna give you different data. So it's like as if you perform the usual experiment, you're gonna have like some data. If you do the interventional rounds, you're gonna have like different data. And if you take all these together and plug into these inequality here, then you have like a higher violation than before in robustness sense. So does this answer your question?
So do I understand it right that you're just collecting more data from the same scenario?
Yeah, more or less. It's in practice, it's not the same scenario because you're doing something different. You really, as if Bob is not measuring his system, or he measures but sends some other information that's not related to his measurement outcome as before. So this breaks some correlations that you had before. So the data is going to be different. It's going to be qualitatively different in this sense. Okay.
I'll have to ask you more later.
Okay.
Thanks. Any further questions?
Nice talk. I am always curious about this thing. Whenever you try to do your best to get quantum violations in network scenarios, and by best is to use maximally entangled states and maximally entangled measurements, you fail. So we always find that some resource has to be partially entangled, typically measurements. Do you have any intuition on why is that so, or any comment?
No, not really. Maybe it's because it's too symmetric when you use like highly entangled states, like maximally entangled states. For instance, the marginals are always, the one-party marginals are always like uniformly random. So this is, I don't know, this, you lose something in that, okay? So maybe that's the reason. But I don't know. It's the same here. If we perform like a maximally entangled, if Bob performs a maximally entangled measurement, you're not going to see anything. You really need to have like partially entangled measurements, yes. But yeah.
Up there.
Hi, Rafael. Nice talk. I wanted to, just to be clear, when you do the experiment, okay, in order to model the fact that Bob is sending the information, what you do is simply just take the outcome and then you feed it into Alice, no, or and Charlie. But then that's fine. And then indeed you don't need the choice, freedom of choice, no. But what you do don't you need the freedom of choice?
What, sorry?
When you do, when you really actually put something else, right?
That's true. Yes. Then I agree. Yes. In the interventional rounds, then you have to choose the outcome somehow. Yes. Then you have to like throw a coin. Then I agree.
Okay.
Yeah. Yes, also, yes. But okay, in my defense, you don't have to perform the interventional rounds, okay? So you already have non-classicality without the intervention. Okay? So my first claim, it still holds.
Okay, further questions? Maybe quick one from my side. So you showed that for 3 observables, you have 3 scenarios basically. And what do you expect if you go to more? Do you expect a much richer structure of scenarios? Have people look at that or
not me, but Marina has. So yeah, Marina is the expert on like 4 observable variable scenarios. She knows all of them. Yes.
How many scenarios do you have for 4?
How many?
Thousands. Okay, because here there were 3, no? I mean,
sorry. Yeah, maybe later I can show you some pictures. You have like thousands, and you can organize them in hundreds equivalence classes,
Mhm.
and you know that there are hundreds that have quantum classical gaps, like that have quantum advantage.
Okay, so
Not
it-
all of them,
Mm.
but there are hundreds.
So it really explodes from 3 to 4.
Yeah.
Okay, so let's thank Rafael again for the nice talk.
Thank you.